Yeah, good morning, good afternoon, good evening, depending on from where you are joining. So it's a pleasure to have you all joining my talk. So I would be covering an overview of what are the protocols which has changed from 4G when we move to 5G. As we have only 1 hour, so I would be trying to just compare it with the 4G protocols and standards. So I'm assuming that all the listeners have some basic understanding of the 4G protocol. I'll also spend some time on the effort which was done through TSDSI towards 5GI, and then what do we expect to happen in future. So my webinar, I would start with first 5G market. We all need to get motivated ourselves on why we should be working in the 5G space and what's the market size, what are the estimates from the research analyst organization. I will just look into the key use case which are getting deployed. There may be other use cases uh, which would get popular, like it happened in other generations of wireless technology later. But the first use case has been on the FWA. Then I will get into deep dive on all the protocols, but I will compare it with the 4G protocol. So I will be just explaining the delta. I'm assuming that the other things, I'll just say the other things remain same with respect to. Last but not the least, I will just explain what is 5GI, which was done with the help of TSDSI and Indian government, and it became part of IMT 2020. So this is an additional RIT which has been approved as part of IMT 2020 in addition to 5G. Then I'll just look beyond 5G and 6G, what's happening and what are the key expectations coming out from that technology. So first coming to the market, okay, as per Omdia, so this is earlier known as OVM. So you can see that over starting from 2020, we are going to see a consistent growth in the RAN number. So overall, the numbers would be around $35 billion. But we can see that infrastructure market, especially the RAN market, is going to shift from 4G to 5G. The older technology, whether it's like 2G, 3G, there would not be any further investment. Many places it's being shut down completely. If you see what has happened till date, this is as per the latest report. Most of the 5G launches you can see has happened in Asia Pacific and Europe, with Western Europe having 47 5G launches, Asia Pacific having 32. And we are seeing launches across all the other continents as well. And if you see from a specific use case, one of them has been the fixed wireless access. This is mostly done on millimeter wave, and that also has been happening in parallel. So if you see the numbers from sort of like 25% of those deployments in Western Europe is in FWA. Something similar numbers are happening in other geographies as well. Coming from the technology perspective, from what has been happening in 3GPP, the release 16 got completed in June of last year. Work has started on release 17 in further enhancing the 5G standard. What I would be covering is release 15 and 16, which constitutes the 5G, and then explain the protocol specifically with respect to 15 and few things on release 16. Just to start from the basic problem of how do you connect to internet. All of us, and I think most of us has a smartphone, so 50-60% of the global population now have a smartphone. Most of us are connected. And it has reached a stage, if you are an Avenger fan and if you know a character called Rhino, there are some studies being shown that we are actually having a projection coming up from the back of our neck, which would more or less make us rhinos going forward. Hopefully it doesn't happen, but the more we consume on phone, we are actually needing more and more data, more and more throughput which is needed. As most of us are working from home or learning from home, we are all mostly connected on Wi-Fi access point, whether it's Wi-Fi 5 or the earlier version, it's 4 or 3, or the upcoming versions, Wi-Fi 6, 6, 7. Uh, or you could be connected on a small cell or a pico cell, which would be based on LTE technology. So it can be few LTE unlicensed as well is happening. So at home, you would be connected through one of these. If you are stepping out for something, you would be connected on one of the 3GPP technologies, whether it's 2G, 3G, 4G, or 5G. Inside your home, you are connected on technology which uses unlicensed spectrum. And here the expectation is you are basically moving around in your house. So you are mostly a nomadic user. You are not moving at very fast pace. Step out, and if you're moving on a car or a train, etc., you would be connected on a 3GPP technology. Most of these are sub 3 gigahertz frequencies, which are widely deployed by the operators. The small cell which you may have near your home on a small tower or pole, etc., would be connected to the macro base station on a microwave backhaul link, the MWB link, which operates in something like 7 gigahertz to say 15 gigahertz, 18 gigahertz. So that spectrum is what earlier has been using. Now there is an effort to, in case of 5G, to use a higher frequency band, the E band, etc., to the backhaul, in case you are not able to take the fiber to the small cell location. Macro cells are mostly fiberized. And the macro cell operates in a licensed spectrum, so you need to get permission from your government policy, government to get to operate in the licensed spectrum. So most of the places that spectrum is allotted to auction, but it can also be allotted to you based on other mechanism. If you are at offices, which very rarely we are now doing, most of us are working from home, then you have a specific connection, which would be fiber, but you would be running some higher security protocols like VPN, MPLS connectivity, which provides higher security. So those connections are another mechanism where you can connect. But within that enterprise, again, there is an effort to take away all those switches and your RJ45 cables and make it a private LTE network or a private 5G network. But it may not be applicable for a small apartment or a small SME building, but mostly for larger factories. Even that is moving to wireless, whether it's 4G or 5G. If you are at home and you are having a fiber connectivity, you have another option called PON. So the initial one would be GPON, but you can get other PONs like XGS PON, etc., where you would be connected till fiber either till the curb location or the bottom of the building, or directly to your home. And that would be connected on GPON initially, and then later with XGS PON and NG PON. So this is another technology which is parallelly happening. All of this can connect to a backhaul network. These are mostly fiberized network running with partly on IP/MPLS, partly on Ethernet, but all of them are carried over a WDM network depending on the capacity which you need to do. Then it connects to a core, which does all the authentication part of it and helping you to connect to the internet. So this is the end-to-end architecture view on how do you connect, and it is only mostly about internet. How do you connect to the internet? With 5G, what changes first is that you have now an infrastructure layer where you have the backhaul. In addition, you can have either proprietary equipment running your 5G stack, or it could be which is either in a CRAN or a distributed RAN fashion, or it could be a virtual RAN based on ORAN, etc., which are getting popular, but that can run on a COD server. It still provides internet, so you will still have an internet slice. So best effort slice still continues to be there. But in addition to providing the broadband connectivity on your phone, if you are on a train, especially if you are going to Japan for the Olympics, which is supposed to happen, a new train is supposed to come, which is supposed to move at 500 kilometers per hour. You will be able to get connected even at that high speed with 5G. Other thing is that if you are going to buy your Teslas, and if you are completely in the auto mode and you have all your traffic signals also getting to talk to your car. You may be able to like stop at the vehicle. Even if you forget to apply the brake, the car would automatically talk to the infrastructure, to the traffic signal. As soon as it sees the red signal, it will basically stop the car itself without you applying the brake. So that's one of those key applications which is being considered as a main use case, and that needs few part. One is that you may have an IoT slice which is for tracking your battery, recharging your battery, etc. And you can managing that slice. You may also need some ultra reliable low latency slice. So in addition to vehicle to V2X, vehicle to everything application, there could be other applications related to industrial IoT. So there are some factories which are now being opened, especially in developed countries, where it's completely, there is no person actually attending at the shop floor. People are either remotely operating it or it's completely autonomous. Going forward, additional protocol enhancements are being done so that you not only can communicate with device on the ground or on the part, like on the ground level, but even devices like drone which are moving up above the sky. So that's one more application which is coming up. Recently, Elon Musk launched another device, a Neuralink, which basically can do brain to computer interface. So you don't even have to use your finger. You have to be uh, having capability to move around, etc. So you can just think and maybe move things around, shop if you want, without even actually having to move the finger. So you can do things even faster than what you have been doing with 4G from a user perspective. So once this happens, maybe you need to reduce the latency further, except that this needs to drill a hole on your head. So depends on your personal choice whether you want to drill it uh, or not. So whether you are happy with your finger or you want to drill a hole and start thinking and just move like all the shopping directly. So coming back to what has happened and what constitute 5G. So it all started with ITUR defining called IMT 2020. So that defines the basic minimum targets which has to be met for the fifth generation of IMT 2020 standard. So the user experience data rate had to be scaled up by a factor of 10, the peak data rate scaled up by a factor of 20. So these were all the target. Spectral efficiency had to be improved at least 3 times. And we had to now, as I mentioned, handle trains which can move at 500 kilometers per hour. The radio latency had to be brought down by a factor of 10. Each of us are supposed to have 10 times the devices which we have. A lot of us are already having more than one device at home. So you needed to increase the connection density. And each of the connections which you have need to handle a lot more data rate. So you need to increase what is called the area traffic capacity, that by a factor of 100. While doing all this, you have to also ensure that the cost of the services remain constant. So the operational cost should not shoot up. So they have reduced the power consumption by a factor of 100. In addition to all of this, India at least tried to add an additional use case called the LMLC, which I will explain later. This should help, at least in rural area, to improve the coverages and at least like a 3 dB improvement in uplink, especially from an uplink perspective. So what is 5G? So whatever came in 3GPP release 15, so this has a new physical layer called new radio NR. It enhanced, it's using most of that what was defined in BIoT related stuff, which was defined in LTE for the MMTC part of it. Other enhancements to use this NR even in unlicensed spectrum has been added. Slicing comes in, the one which I explained in the initial slides. This is specifically with the 5G core, where they have added a slicing portion to it. And then it's moving to a service-based architecture. I will explain a bit of it in the next slide. Even this release 15 was not like we have one standard. So initially there was an early drop. This was basically for the users in developed countries. They started with what is called a NSA option. NSA is non-standalone. The non-standalone option needs 4G to simultaneously operate. So the initial control signal, etc., through 4G. So this is called also called as option 3. This got completed in March 2018. Then there was a main drop, which also came up with standalone 5G. So the 5G core as well got standardized in the main drop. So you have an option 2 there. And there happened a third drop, it's called the late drop, which took care of multiple other options, option 4.7, which are related to how the operators wanted to migrate from their existing 4G to 5G. There are different options provided. So in case you are a operator who is already having a 4G network, or is a brownfield operator, an IoT drop based on NSA may be useful. And if you are having an option of starting completely afresh, then you can straight away move to a standalone 5G. It got further streamlined in release 16, where V2X, etc., got enhanced, industrial IoT got added. So many more verticals issues related to that got added. The NR-U got completely standardized. And then few additional things came into the discussion, which is like, can I use some of my spectrum to do my backhaul? So one of the issues which was found was that all the 5G sites, because 5G anyhow doesn't cover the same area as 4G, you would have to take the base station even deeper. So how do you backhaul? So can I use some part of my spectrum to do the backhaul? Maybe the same spectrum, or could be on a different band for backhaul. So that got standardized, and even the ability to use satellite as well for backhauling or as a relay is also being discussed. That's the most happening part in the 5G, which is like, can I extend the terrestrial network based on 5G to non-terrestrial network as well? And you would have heard of all this Starlink, etc., providing capacity through satellite. So that's another thing which is getting at least studied and then eventually getting standardized in future. So what's the first deployment model? So the first deployment model is to have 4G EPC to continue, migrate your core from EPC to 5G initially, at least the brownfield vendors. Your handset actually would have dual RF chain, one connecting to 4G. So all your initial control signals would come through 4G. And in some case, even your uplink may be on 4G. Only for your high throughput, high data link connection, you would connect over for 5G. So 5G is more or less like your Wi-Fi hotspot, but with much larger coverage area. Once you connect to the 5G, within that data, it may be sent to a 4G base station through the X1 interface or the X2 interface, or directly connected to the EPC. So depending on that, there are three options, option 3, 3A or 3X, and 3X seems to be popular. Handset, so the handset would have to support 5G, and I think all the handsets are already coming in the market. Even the prices has been coming down quite rapidly, so hopefully we'll see 5G have handset crossing the threshold to make it more viable. Mostly it's a dense urban scenario for 5G, and then as I mentioned, we are actually having a dual connectivity with the assumption that UTRAN is the main candidate or master, and then is the secondary or the slave device which connects, which is how it operates. So the 5G, say for example, if your phone has only VoLTE, that can still continue to talk over 4G, and then 5G can simultaneously give you the broadband thing. Going forward, we will have the SA deployment. So if you are a complete greenfield guy, you can start directly with a 5G core. The 5G core would be managing all the 5G RAN, and 4G if you have, that can continue to be operated from EPC. Or you have an option to migrate all your 4G base station by upgrading your band side of it and making it NG-NB and then connecting to the 5G core. What do you get in addition to the 5G core? So it's first thing in 5G core is that we are moving away from a lot of signaling protocols to HTTP2 and JSON. So this should help all the new employees or something, or new students who are coming into the market who are more comfortable with HTTP2 and JSON rather than signaling. It also brings in a vendor agnostic API. So earlier, each of the APIs, depending on who is the RAN vendor or the core vendor, had a separate APIs. Now the APIs would be vendor agnostic. As I mentioned, you will have a slicing function. So at least you will have 3 slices: EMBB, URLLC, and MMTC. And you could build more slices depending on how you want to split out. It's actually a service-based architecture in the sense that you have something called a NRF, a registration function, a network registration function, which would allow the producers to come and register at their own period of time, and consumers can independently register at their own period of time. So this is de-linked in the sense producer and consumers are independently can come and register their network function at different point of time. And there is a network exposure function, which would, from where you can pull in the data of the traffic, type of traffic which is flowing, etc. And that's how the whole 5G core has been developed. From the architecture perspective, there is a segregation of control and user plane. So all the user plane related function has been converged into a single function called UPF. So this can be a virtual UPF, which can run on a standard COD server, and it can scale depending on the throughput which you need. Here, the UPF basically converges both the S gateway and P gateway of 4G, the data plane function. The control part of it, the S gateway and P gateway, has been moved to what is called the session management function, SMF, in addition to some part of the MME. The AMF, which was related to the HSS and MME part of it, is separate, and authentication, the HSS part of it, is kept separate. So you have multiple network functions. So these are all software. They communicate with each other through a service-based interface, etc., with some HTTP2 JSON signaling, rather than signaling protocol. From the RAN, the big change from 4G to 5G has been that the interfaces have migrated from S1 interface to NG interface. As I mentioned, the MMES gateway, etc., has been converted into AMF UPF. So that from 4G core, which was called EPC, Evolved Packet Core, we are moving to 5G core. The EUTRAN, which was the NGRAN portion of it, consisting of all the base stations, etc., we are migrating to NGRAN, with interfaces like NG used to connect to the core, and XN for inter-base station communication. And your eNode B, the 4G eNode B itself can be upgraded, and they can also communicate to each other if it is an NG NB over XN interface, or can connect to the PNB. What are the key changes? One is that the frame structure remains more or less same in 4G. So it's a 10 millisecond radio frame. It is further divided into 10 subframes. So you have 0 to 9 subframes, each of 1 millisecond. The slots, you have 4 slots, and within slots, you have a concept called minis. You have the symbols, the OFDM symbols, and you can create something called a mini slot with 1 or maybe 2, 3, or 7 symbols. So that's how you are reducing the latency part of it. And then at a HARC level, at the MAC layer where you are at the HARC, the earlier HARC mechanism was that if you basically send a signal, you get the response back after 8 TTI. Here it's built into the system whereby you can get the responses faster. So the HARC mechanism is faster, so you don't have to wait till the 8 slot. So that's how, from a HARC perspective, also things has been speeded up. The additional thing is that there is something called a primary synchronization signal and PSS and SSS, and along with PBCH. You can see that various carriers of 24 PRBs initially has been allotted to do the synchronization as well as the PBCH. So you get an information about the network through this mechanism. So all those guys can first sync it up based on this synchronization PBCH information. Conceptually, and from a waveform perspective, it is still OFDM, and the multiple access is based on OFDMA. You have concept like orthogonal subcarriers and you have guard intervals between the slots. So each of these are symbols and time domain, and you have subcarriers. So each one subcarrier, one symbol basically becomes a resource element, and multiple resource element forms the resource block. Conceptually, it's same as what we have in 4G, except that you have now this concept of mini slots. So you can even do the scheduling at a mini slot level, and that's how both from a, say, for example, NBA IoT application may need only a few mini slots. That's the change from the OFDM perspective. So you can now allot at a symbol level rather than at a slot level, which was the case in 4G. If I were to compare 4G with 5G, so the 4G downlink was CPU OFDM, cyclic prefix OFDM. So same thing continues in 5G, but in uplink also I can use the same CPU OFDM, or you have an option to use the same 4G uplink mechanism of DFT or SOFDM. In addition to BPSK, QPSK, and MQAM in 4G, we have now the 5x2 BPSK, which is better from the PAPR perspective. This is the modulation scheme from the 5GI perspective, which was slightly modified, some not doing a DMRS filtering, etc., to improve the coverage for rural area. That was what went from India contribution to TSDSI. And you can go up to 256 QAM. So potentially with a good signal strength, etc., you can get higher. From a coding, we have moved from turbo coding to LDPC for data, and thanks to China, we have some additional work to do on the polar code on control and PBCH. So control and PBCH moves to polar coding, and data goes to LDPC. So unlike 4G, which had same turbo coding both for data and control, here we have separate coding scheme for data and separate coding scheme for control and the broadcast channel. Subcarrier spacing, which was just 15 kilohertz in 4G, now we have multiple options from starting from 15, and all the other option you can see is actually 2 raised to n times 15 kilohertz. So that n is actually called the numerology. So you can have multiple numerologies. So 15, 30, and 60 are for FR1, 60, 120, and 240 are for FR2. FR1 is frequencies between 450 megahertz to 60 gigahertz, and FR2 is above 60 gigahertz, but mostly from 24.25 to 52.6 gigahertz. Why you needed to move to higher subcarrier spacing for at least FR2 is basically because your DSP technology, the FFT, also is like maximum you can do 4,000 subcarriers. FFT means, so effectively you may not be able to do 15, so hence FR2 15 may not be applicable. From a because you are now getting much larger bandwidth, whether it is in FR1 or FR2, FR1 can go up to 100 megahertz, FR2 you can get up to 400 megahertz. The number of PRBs, which is the physical resource blocks which you can get, also has gone up. So from 1,200 you can go up to 3,300, exactly 3276. Slot length, which was 14 symbols in 1 millisecond in LTE, further modified to 7 symbols in 0.5 millisecond, reduce latency even in 4G. Now you have all the options 2, 4, 7, which are called mini slots, or 14 symbols for within a slot. That's how you can do the slot, the concept of this mini slot which came. MIMO, you can do 8x8. In duplex, 4G only had TDD and FDD. In addition to this, we have a flexible duplex which is possible in 5G. There are 56 formats which are defined. You can basically do the static or dynamic scheduling. So if you are doing dynamic scheduling, you are informing it the DCI. DCI means to inform which of those formats to be picked up. Additionally, if you see the additional channels in 5G, in addition to what has already been defined for 4G, there are PSS, SSS, the primary and the secondary synchronization channel. This would be useful for initial synchronization. Then DMRS, which was earlier defined only for PDSCH, is now expanded to for all the other things, PDCCH, PBCH, and PUSCH, so both uplink and downlink. So this would be useful when UE is not in the connected state. So either in idle or idle state, if you are there, DMRS would help. The CSRIRS, which was used by UE in connected state to provide the measurement, is now refined. It also helps for refinement of the beam. So if you are connected on a particular beam and if your signal strength shows that the beam adjacent to it is better, that can be found out through CSIRS, and then you can connect to a appropriate beam. There is a PTRS, phase tracking reference signal, which got added. This is completely new. So this would allow us to do phase tracking. So you can track time and frequency much more accurately. You have a mechanism to do the phase noise compensation, both for DL and uplink slot. Similarly, the PDCCH got enhanced to do the slot frame indication, which I mentioned that you have now a flexible duplex, which is possible. You have a preemption indication. This is basically if you want to preempt a frame, this would be especially used for IoT, then it could be used for that. And the UE would do it only if RRC request to use it. The next thing was about bandwidth part and a supplementary uplink got added in 5G. You can configure up to 4 downlink and 4 uplink bandwidth part. It's initially signaled over PBCH, the broadcast channel, and then you can configure your numerology. So you can each of the bandwidth part can have separate numerology, so different subcarrier spacing. You can specify the frequency offset where it starts, starting from the starting point, and what would be the bandwidth size of the PRB. Similarly, there is a supplementary uplink, which are usually on the lower frequency band, sub-gigahertz band, which can also be used to increase your uplink throughput, which was one issue with 4G. So that option also comes up. This also would need that supplementary uplink allocation happens from the policymakers, etc., to get the additional supplementary uplink. How does it help the UE? One is that you don't need to work on the full bandwidth. So you can work maybe on your 5 megahertz or 10 megahertz. So the UE need not work on the full bandwidth. So that helps to not only reduce the cost of the device, but also reduce the energy consumption while it's operating. So you don't need to completely operate on the full bandwidth. You can have separate numerology for different bandwidth parts. So some of the, say for example, you have a slice, which is like NB-IoT or the vehicle to X, which can use maybe the initial part of the network, maybe operating in a even say 15 kilohertz. The higher part of it, your EMBP part of it, may be operating and say 30 kilohertz sub-carrier spacing. So that option is possible because now you have bandwidth part, it would decide how the UE operates. It also helps to operate in a non-contiguous spectrum. If when operator doesn't get a contiguous spectrum and you have pieces of spectrum which you get, you can ensure that some part of your devices that can operate in a part of the spectrum and the other devices can. So maybe you can put all your Apple devices in some spectrum and all your non-Apple devices in spectrum. This also in future help in forward compatibility. So once you define future thing, you can easily migrate. So your old handset can work with the bandwidth part with the lower subcarrier spacing, and future devices can work at higher. That's the advantage of having this bandwidth part. Other thing which came up was massive MIMO. This is especially useful in FR2 because at FR2 we don't operate like how we operate in sub 6 gigahertz, where you have multiple paths, etc., which would help you to improve. And here, the only way to increase your quantity of signal to the user would be to form narrower beams. So if you put enough antenna separated by lambda 2 both in horizontal and vertical, you can get more beams. So you can get 8 beams or something, 8 independent beams tracking different set of users. So instead of having one sector catering to 120-degree and all the users connecting to that sector antenna, you now have different beams and each user can connect one of the beams. One user will be connecting to, as I shown, the green beam, and the blue and orange beam can be catering to other users. So the narrower beam has one more advantage. When you do it, you get an antenna gain. So that would ensure that at least the coverage wise, we are not losing a lot of coverage because as soon as you move higher frequency, any of the coverage drops. This would allow independent beam to have little more coverage compared to if you are not doing a massive MIMO. and you are sending more energy per beam because you are making it so from 120 steradian, which you are doing, say 120 degree, which you are doing earlier, you are coming to a 15 degree. That would help to put more power in the same smaller beam size. And it helps spatial multiplexing, whereby one user can connect to the blue beam, another user can connect to the green beam. So if you have multiple such beams, say if you have 8 beams for each of these, your area traffic density is going up because I'm using the same frequency to in each of the beam, and then you are allowing multiple users to connect in the same beam, so increasing the area traffic density. You have multi-user MIMO, which was there in 4G also. You can connect more users within the beam. You can have more users connecting using the multi-user MIMO. How do you build it up? You can do it completely analog beamforming, whereby the phase shifting which you have to do for ensuring this beam formation, constructive beam formation along one direction, can be done using analog mechanism, whereby we do the completely in digital domain by doing the matrix manipulation in the digital domain, doing the phase changes in digital domain. But what seems to be popular is doing it in a hybrid mode. You do partly in analog, partly in digital. So if you see how do you work in this scenario, I'm just giving a broad hint. It's a TR3880. So if you have a handset, you can connect to each. So each of the beam would be indicating the SSP to the signaling block, whether signaling block number. So if suppose I have a handset, it sees that the green signaling block 1 from the transmit receive pair 1 is better than SSB2 signal from TRP2. The handset can inform the same, and TRP1 would in turn get connected to the handset. So they have signals from SSB1, 0 and 2. So these are some parts. So initially you have to select the beam. Then if you are on the connected state, you basically, if you want to connect to one of them, you have to inform the measurement thing, and then you can refine first on the transmit side and then on the receive side. And then the process is defined that the P1, P3 process, the beam appropriate beam refinement. So all this becomes part of what is called the beam management. Now stepping to 5G system overview. So as I mentioned, you have GNB, which roughly does all the things which ENB used to do in 4G. Then, as I mentioned, we have split up the S gateway, P gateway, MMP, and PCRF is now PCF. Other things have been redone in AMF, UPF. UPF is for data plane. AMF, SMF is for your control plane and session management. From an end-to-end perspective, the physical layer continues to do all the coding part of it, adaptive modulation and coding, all the MCS, input, etc. In addition, as I mentioned, we do 256 QAM. MAC, we have the HARC happening. The RLC will do the ARQ if it is in the AM mode. The PDCP will do header compression and in addition ciphering and integrity checks, the security related aspect. An additional layer which got added was SDAP layer. So that does QoS. This would allow end-to-end QoS all the way till the devices to be stitched and like the mapping happens both from a radio bearer to the bearer side of it. Same thing on NAS continues to do SI, paging, and RRC. So I'll just explain it. 2-3 slides. If you look whether downlink and uplink, it looks more or less same. The functionality wise, segmentation ARQ happens at RLC, the ROXC security happens there. The new SDAP layer got added, which is for QoS flow handling. So you map the QoS flow into the radio at that layer. This happens both at the base station level and at the UE side of it. On the uplink side, it just swaps. So the uplink side, you have the QoS handling again coming up. There is an SDAP layer. So if you see the delta with respect to 4G, SDAP layer got added. So you have a QoS flow mapping where radio bearer and QoS flow ID in both downlink and uplink packet. From PDCP perspective, now the PDCP can map PDUs to more than one logical channels and send it over different component carriers. From a MAC perspective, in addition to doing all the other things like error correction using HARC, the padding, etc., you are doing some part of the RLC work, which is 5G concatenation can be done in Mac, and so this is just to reduce the processing latency, which got added. And an additional thing which got added in the Mac and RLC part of it is related to the beam management and transmission, the new transmission mode which came up, and the ability to handle multiple different numerologies. The RRC layer does all the paging related thing. In addition, it basically does the dual connectivity part. It can connect both to LTE and NR. So those modification release of dual connectivity is handled by RRC in addition to what it has been doing for 4G. An additional thing got added, state called RRC inactive state. You don't have to go from RRC connected to RRC idle if you are not using it. So you can be in an inactive state where you are still your UEAS context is still kept in the GNB, so it's not completely. This helps you to come back to the connected state faster. On the paging side of it, this is basically needed if you are in either RRC idle or RRC inactive stage, and then whether RAN or the core have to talk to you. So that can be a RAN initiated paging or a initiated paging. The DRX or the discontinuous reception cycle can be specified. It's a configurable parameter. And how many times you can do this paging within that can also be decided based on the UE ID. So UE can connect on different point of the DRX cycle. That would allow you to distribute the UE load different paging location. The paging itself can be a single slot, a subframe, or a multiple slots. Can be even OFDM symbol based at this level. Key thing is that 5G, the paging is usually used for triggering the RRC setup, the public warning system, the earthquake warning system. Some information modifications are done through DCI, so they are not using paging. From a random access perspective, you have the same thing, similar to 4G. You have 4 messages, message 1, 2, 3, and 4. So this allows either a contention-based or a contention-less option. So contention basically pick up one of those orthogonal symbols and then try to connect. And then contention-less is there, and there is a process. So 1 and 3 are trying to be combined as message A and B. So from message 1, 2, 3, 4, we are moving to message A and B. Part of it. The scheduler operation is basically similar thing. So you get the UE buffer status informed to you. So that can be set up. If you are reporting it very frequently, then your signaling loads are higher, overheads are higher. Depending on that information, the scheduler in the radio allots you to use up the appropriate resources. And the resource assignment also happens. It tells you whether you get the full slot or a mini slot, etc. gets allotted based on your buffer status. From a QoS perspective, as I mentioned, you can have multiple QoS established, multiple PDU sections established all the way to EP. So you can have your Netflix on a separate QoS flow compared to your best effort browsing being on a separate QoS flow. You will at least have one DRB, one or more DRB can be set up. So these are all more or less same as what you had for. Now that sort of ends the 5G related protocol related thing. I'll just step and explain what happened in 5G effort which happened from TSDSI and supported by Government of India. So as part of the national digital communication policy, there was a focus on starting a standardization body from India, like the ETSIs and the ANSIs in US and Europe. This was formed in January 2014, and then we started working on it. There were multiple issues. We got delayed, and we finally gave a LMLC requirement, low mobility large cell requirement. It became a mandatory test requirement, test configuration C in the requirement document, which is IMT 2020 M2410 2412. Then we actually did, we tried to give the solution enhancement through 3GPP. For some reason, it didn't go through. So we then directly went to ITU and submitted an India's interim RIT, SRIT, and then we gave a final RIT in 2019. This now got standardized by IMT 2020. We have completed the complete IMT 2020 process, and we have named it as 5GI as the alternate 5G thing. So in addition to 5G, there is a 5GI now approved by ITUR in the IMT 2020 process. So what is the key difference? See, when we looked at the rural area, it's basically a coverage issue in the rural area. We in India, mostly in rural area, are like not used to very high speeds. We may have it in future. We don't have very high speed passing through the rural area. So most of the rural requirements in the other one was not so much focused on a scenario where you have a very low mobility, but we want to increase the coverage in that scenario. So we did this study. This was from an NHA published study on how much was the speed of different users. So we can see that most of the users are basically sub 30 kilometer speed. So based on that, we actually did an analysis of all the Gram Panchayats, because there is a BharatNet effort which is happening from India to connect all the Gram Panchayats and eventually to each household. So each Gram Panchayat maximum ISD was 12 kilometer. So there was a consensus building first in India, then we brought it down to 8 kilometer because it covered more or less all the Panchayat. Then there was further consensus building across countries, and then so the developed countries didn't want to have larger ISD. The developing countries, including Russia, wanted a supported it and all that. And finally, it sort of a compromise of 6 kilometer was reached. That was related to the requirement, and that requirement became part of IMT 2020 requirements. And then later we went to ITU again with the TSDSI radio interface technology. So this is an improvement over the global 5G standard, which was released by 3GPP release 15 and 16. So the idea here is that with a modulation scheme where we don't filter the DMRs, etc., we have shown that it works. The proposers, which is basically IIT Hyderabad, IIT Madras, and CIVIT, have shown that it improves by 40%. Similarly, there were small enhancements done so that your bandwidth utilization went up by something like 11% on because of and then PCI payload changes helped 19%. Spectral efficiency was sort of improved, and signaling load was sort of reduced. So these are small changes in addition to that improvement in coverage which was done, and that became a IMT 2020 approved standard. This is now a 5GI, and hopefully we can do a lot more improvements with 6G, and hopefully we would like to work through the system and see how it works out. Hopefully it becomes part of 3GPP itself in future. Otherwise, yeah, we still go to ITU, etc. So what happens in future? So in future webinar, I would expect to be in each of your home or offices or school, wherever from where you are attending. So the 6G webinar should be more about hologram. So this needs very high data rate. So if you are representing without any compression a 6 feet tall person, you almost need 1 terabits per second. And if you want to do it over wireless, this is a huge scaling up which you need from the data rate. What are the other use cases of hologram? You can have your digital twin, your own digital twin, or all the objects which you see around. If you want to feel it before you buy from, say, Amazon or some other thing, if you want to feel the object with 3-dimensional rotation, feel it before buying it, that should be possible. The telepresence, etc., which is happening today in 2 dimension, hopefully we should be 3-dimensional. Your schools, webinars, etc., which is now maybe a plain video, you should have real hologram, and hopefully you can even shake hands with the speaker and other way around. And the key application would be in robotic surgery, where you can do a 3-dimensional MRI and CT scan, so the doctor can rotate it and see how to use it. So how do we see it, at least from Tej's point of view in future? So you would have a lot more of the cloud getting deeper. So we are already having applications like MEC, Multi-Access Edge Cloud. You'll have even deeper access clouds, etc., which would be standard server-based thing, where you could be able to run part of it depending on the application, depending on the slice, latency requirement, etc. Some part of it would either run on access cloud or edge cloud. And you will have backhaul network and a front haul network. This would in turn connect over fiber to the nearest electricity pole near you. So there would be fiber termination to each of your electricity pole near you. So in addition to electricity poles carrying the electric lines, you will have optical fiber also. It's already happening in many places, at least in India. And then if some small location you can't connect over fiber, you have this integrated access and backhaul, which is being standardized starting in release 16 and would be completed over release 17, etc., which forms what is called the beyond 5G part. Suppose you can't even reach by IAB, if it's far off, you can use your non-terrestrial network, NTN, your satellites, etc., to connect to that pole, which would then operate maybe in a terahertz band. You should basically be building homes in addition to laying fiber to, in addition to having your electric poles, you should basically carry fiber to each of your. The only thing you have to make sure is that if you are carrying fiber, don't have too much bending, because that would have a lot of loss. Prefer to have straight lines on the fiber. So you should start planning how to lay your fiber in your home. If not, the other thing would be that fiber termination at each straight poles would basically would be able to provide you connectivity to that poles. In addition to laying sewage lines along the sides of road, you should also plan to have pipelines or the ducts to carry your fiber along each side of the roads. So these are all some aspect which needs to be looked beyond the technology. If you have to get into by 2030, we should be fully pervasively connected. You will be moving into terahertz frequencies, and each of your street light, maybe you don't need a light now because all your phones have a like light already, and your street light can be converted to an unlicensed access point or a licensed access point using either the 5G NRU or the Wi-Fi. At home also you are connected on that with that same technology. Suppose you can't put the fiber, there is in 6G something called reconfigurable surfaces are coming up. So you can get it reflected. So you basically, because you are at higher frequency, you can just divert that signal and get it to your room through a proper means. So those technologies are coming up. So that would become part of the 6G development, which is also happening in TSDSI right now, as we speak on coming out with the use case and technology. And that brings me to the last slide. Basically, it tells you all those references within 3GPP, which you can read. With this, I end my thing, and any questions, you can just put it on the Q&A window.